We are live. I'm going to stop sharing so you can share, Brad.
Sure. Let's see if we can get this going without any difficulties. Be nice, like, see if we can do that right off the bat. Okay, let me get into present mode.
Nice.
Awesome. Can you guys see that?
Yes, definitely.
Awesome. Okay. So right off the bat, I feel like something out of the way. Yes, Julie was very kind in the intro and introducing me as a developer at a company named DataStax. We are a NoSQL company, and I am the least qualified individual at that company to talk about NoSQL. So you guys are stuck with me. I'm learning this as I go as well. This is something that's very new to me. That's part of the reason why I looked at DataStax and joined them, was kind of like the stretch sometimes in areas that I'm not super comfortable with. I am definitely of the relational database persuasion and history. So that's where I come from database land. So NoSQL is very new to me, and I'm hoping that through that lens, this is helpful to you guys as an intro. I do want to start with that disclaimer, though. I'm trying to make sure that I got everything accurate. If I have any corrections after the fact, I will, of course, pass those along. But I think because we're keeping things pretty basic today, we'll be okay. If there's not any immediate questions, I'll launch right into it. Yeah, I don't think so. I think we're good. So this is an intro to NoSQL, overly simplistic introduction to deceptively deep topic. And we'll get into why in a minute, and hopefully you'll see pretty quickly like how this is a tough talk to nail down in a very short period of time. So we're not going to get super far, but I'm hoping that you guys get a good sense of what's going on after this talk. Again, my name is Brad. I work for DataStax. I think that's where we'll keep it for now, but I'll leave my details at the end so you guys can reach out to me, but you don't want to hear about my whole resume. Let's just dig right in, right? Let's take a look at what we're actually going to talk about today. We're going to cover briefly what the kind of definition of NoSQL is, though we'll talk about how that's kind of hard to nail down, what the major differences are between a traditional RDBMS or relational databases and NoSQL, what the different flavors of NoSQL is. Spoiler alert, there's not just one NoSQL solution. In fact, it's varied. There's several different kinds. And we'll briefly talk about how you, after you're armed with some of that basic information, how do you decide what type of database is right for your application? Sometimes that's tough. And sometimes you can burn a lot of cycles trying to figure that out. So hopefully we can make that an easier prospect next time you start a project. Things we won't cover, we're not going to get into what a relational database is, except for maybe just a real quick overview. We're not going to talk about what SQL is. And unfortunately, we just don't have time for hands-on demos, which actually bums me out. I kind of like doing those. So if you guys go, oh man, that NoSQL flavor is really interesting, maybe we can do some follow-up, either one-on-one or in some other format. But that's our basic overview for today. We got a lot of ground to cover, so I'll launch right into it. First thing we want to do is just kind of get an idea of what the difference is between a traditional relational database and what a NoSQL offerings are that are out there. And real briefly, I promise we aren't going to spend a ton of time on this. And if you do have some questions, we can talk about that in Q&A. But relational databases, generally speaking, you first think of structured data. You know exactly what is going to exist in which table, what columns there are, how those columns are going to expect data, and what they're going to reject if you try and stick in them. In other words, you are tying a particular column to a data type, and the system won't let you put the wrong data in there. You have something called ACID guarantees, which I won't dive into right now, but in short, that's just making sure that consistency is king for a relational database and that your data is making it into the database in a reliable way, or you have reliable feedback when that doesn't occur. When you need to scale up, if you're actually managing this database, if you need to grow the database, you're talking about what's called vertical scaling. You're making the machine bigger and badder and throwing more memory at the problem, more storage at the problem. It's really hard to start scaling traditional relational databases, what's called horizontally or across multiple machines. That's changing and not maybe technically true anymore with some of the more modern offerings that are coming out, but it's still a tough thing for traditional databases to scale like that. Use a SQL. And finally, consistency is king. I can reliably know that if I've written something in a database, it's successful if I'm told it's successful, and anyone that's reading that data back out is going to see what I just wrote to it, what I just committed. I call that out because that's one of the major differences that we'll get into. So let's contrast that. NoSQL databases. Now, I have to put an asterisk next to everything that's on this list right now, because some of this is kind of sort of true for certain versions of NoSQL and kind of sort of not for others. But generally speaking, we're talking about something that is unstructured. I can throw whatever data I want at it. I can change that on the fly. Like tomorrow, I might decide that I want to put different data into the exact same places in my database, and that's okay. It's distributed by nature. It's rather easy comparatively to take your database and replicate it out or move it out to several different database servers. And that's kind of what gets into horizontal scaling right here, where, hey, we can take this database and we can take small, cheap machines and service it across multiple different versions of that, instead of trying to just throw money at the problem and scale out our databases by making our computers bigger and better and faster and more expensive. The big trade-off here for most of these things, though, is availability is what NoSQL databases care about. You want to always be able to hit it and get a response from it. There isn't an immediate guarantee that you are going to get a consistent response when you ask for a certain amount of data. And we'll get into that a little bit more later. We're trading off consistency for availability. And basically what that means is if I have a couple of different people that are connecting to my database and I write a new entry to my database, person A might receive that new write, person B might not immediately receive that new data. Eventually person B will, but maybe not immediately and not consistently. And that's one of the main differences between a relational database and a NoSQL database, is that eventual consistency is what that's called. And generally speaking, NoSQL databases are optimized for very specific requirements and use cases. You get the most bang for your buck when you approach this database or this family of databases with a specific use case and requirements in mind. I know this is a lot of ground to cover. Bear with me. We're going to zoom through a little bit more. Hopefully, in the aggregate, this makes sense, and we can handle some of this in Q&A. But in short, your relational database optimizes for consistency. Your NoSQL databases are going to optimize for availability. Always on, being able to always get something back, even if it's not the freshest and latest and greatest version of that data. With RDBMS or relational databases, you are deciding that, hey, I'd rather go down than produce stale data to a client. I'd rather not be available than not be consistent. And that's the main trade-off that's occurring. I hinted at this. What do I mean by eventual consistency? Eventually, everything that is connecting to the database will get the newest data. There's just no guarantees that you will always get the freshest data when you ask for it. That's in short what's meant by that. And it's a deep topic, so I think I'm going to gloss over from there. But that's in short the main trade-off that you're making. So there's a theme. When you select any technology, when you think relational versus NoSQL, or in a moment when we start talking about the different flavors of NoSQL, we're thinking in trade-offs. What is the best option for me right now, given what I'm trying to achieve? And that might be the type of application you're doing, or what you're trying to learn, or where you're at in your development journey. It really depends. I will link these slides after the talk, but I highly encourage you to read the article that I've linked here, where this think in trade-offs phrase is from. And that kind of expands on this philosophy of like, hey, it's worth flexing the muscle of taking a step back and thinking about, what am I trading off here? There is no good versus evil. This isn't a Marvel movie. Right tool for the job is basically what this is saying. All right, fine. I've been going on for a while. This is supposed to be a talk about NoSQL databases. Like, can we just like get to the thing where we can actually show what this looks like and what I can do with it? Unfortunately, not, because it's not a simple question to answer. I can't draw an either or here. There's different types of NoSQL databases, so we have to go through that exercise first and talk about the different kinds. And we'll start by talking about how NoSQL databases can differ from each other. There's so many different types of NoSQL databases that are out there right now. And even within certain classes and similar families of NoSQL databases, you can have wildly different approaches. However, there are like 4 main data models that we're going to go over. And this is kind of, if you are going to classify and group together a bunch of different databases, you would be grouping them by this, like how the main idea behind them. This also informs like what they're really good at. But within those different data models and those families of databases, they have different ways of interacting with the database. Some have some things that are really similar to SQL. This can feel very comfortable if you're used to relational databases. It can also be a little frustrating when you run into slight differences or things don't behave exactly as you expect, because it's not, at the end of the day, a relational database. Others say, to heck with that, I'm going to have something like a REST API or some other paradigm completely. Usually there's also some language-specific SDKs, like install a Node npm package, and you can interact with the database with certain level of commands. And sometimes it's a mix of multiple things, and you have some choice. If you're nerding out on databases and how these things work under the hood, the architecture can vary. Some use this whole primary, secondary setup that might be very familiar to people that are familiar with how relational databases work under the hood and how are they managed. I'm not up to date on what the correct terminology is. I'm glad that we're moving away from it, but please forgive me for using the old terminology. It's a master-slave setup, and we're moving away from that terminology, but it's failing me what the new terminology is. Some use more of a peer-to-peer model, where all of these nodes are equal. They all have the same. There is no primary, secondary setup, and they can all service the same requests, and they can all spit out the same data. And they shuffle data between each other with kind of like almost a peer-to-peer model, like for people that are old farts like me, back to the Kazaa days and the Napster days. A more sophisticated version of that, but they're shipping data along between each other to eventually get everyone in sync. And then the data distribution model can vary widely. How reads and writes happen, how data gets shepherded along, whether it's over a peer-to-peer model or something else. And this really impacts how resilient your data is and how flexible scaling and distribution is. So finally, we can with all that context, start talking about what types of different NoSQL data stores are, which really gets at the heart of like what's possible and what the landscape looks like and what they're good for. The main types that we'll talk about today are a key value store, a document store, columnar setup. I always have trouble with that word. And then a graph setup. Just double checking my time. Okay. Other data stores that I won't talk about here, but bring up briefly. There's object data stores. Those are really good at like big data. I'm sorry, no, big files like videos or pretty large files. It's efficient at storing those and sometimes getting metadata and searching on those. Time series is really good for like Internet of Things, where I have a sensor that I want to constantly send some data somewhere. And I want to have that against timestamps that have some good precision to them. It also allows you to really do some interesting things within time slices, and that's really good for. And then you have external indexes. That one's interesting. You actually use one of those all the time, every day. Anytime that you go to a site and you have a really nice responsive search that maybe is a little fuzzy, and you type a few letters in and you get way more context than you thought. Maybe it's even predicting what you were asking for. Someone's using an external index under the hood. Almost none of these paradigms, including relational databases, are good at full text search. That really taxes a database. So this is a common use case where you lay an extra database on top of whatever your solution is to enable like some really good search functionality. So that's a common use case for a very specific separate data store. All right, with all those tangents aside, let's dig in, talk about the key value data store. This one's really basic. It's basically a hash table as a service. If you're not familiar with the term hash table, that's in JavaScript, your basic JavaScript object. In Python, that's your dictionary. In many languages, that's your dictionary. It's the one that has like a key and you attach value to it. Now imagine that as its own standalone database where you can just shove whatever you want into the value section, and you have a pretty good mental model of how this thing works. That sounds really simple. Why would you want this? Well, its simplicity is its value. In a lot of cases, particularly like caching, you can really optimize for some gnarly queries that take forever if you didn't reach for something like this. And you can lay this on top of an existing solution and say, okay, that thing's slow. I want to make it faster. I'm going to stick it in this key value table. And anytime that someone asks for this, I can look it up in a really efficient way in this key and provide them with a cache value immediately. That's not the only use case, but that's the most common one. An example of that would be Redis. But yeah, really great at those, hey, I got a key, I want to get my value. Not so great at joining things together. So that's its limitation. But its strength is in its simplicity. Document data stores. All right, this is the next one, and it builds off of our last example. It's kind of this extension of the key value system. Instead of bare values, though, where we just have one key going to one value, we store an entire document. And commonly, that's a JSON document, but really it could be anything. In fact, one of the earliest examples of this was XML. And but you can store quite a bit in here. And usually what you see for this use case is people like to reach for this tool when they're riffing on an idea, requirements are changing pretty rapidly, or they're able to clearly define what the major actions and things that our user are going to do in their website. So imagine like a blog. If I load a blog article, I need to get the post information, the metadata on that. I need to get information about an author, and I have to get information about related comments. In a relational database, I might have to do at minimum 3 table lookups in order to get that, maybe even a 4th if I need to have some sort of pivot table to relate things in between, and do a series of joins. The difference in approach here is you shove all of that information in one document and attach it to some unique key like a post ID. So when I load this page, instead of doing a lot of work to join a bunch of stuff together, I go, give me all that information for that post page, and there I go. It gets really close to how you probably want to interact with this data in your actual application. So that's the main advantage. It also allows for, hey, so-and-so just told me, look, tomorrow I need to add in a tagging system, and we really need that right now. Instead of remodeling the database or the data at the database level, I can just change this in application code, and suddenly I've now added a tag section to my JSON, and we're done. I've done the change at the application level only, and the database is able to accommodate just receiving new data. The downside of this is also its flexibility. This can bite you when this denormalized or shove everything in the same place model can really hurt you if, let's say, Julia decides, hey, look, we're going to add some metadata, and she wants to change something about the metadata of her author information. Now I need to go find all of the articles that Julia's authored, all the things that Julia's commented on, all of anywhere that she's mentioned as an author, or maybe even a user in the system, and I need to make that update, as opposed to just updating one place in a database and having those changes carry out. There's ways to mitigate this, but that's usually where people run into trouble, is when they go, oh shoot, I really do have a lot of related data here, and establishing those traditional relationships is a good thing, and having this traditional structure is a good thing, and me punting on that structure is really starting to burn me. But there are plenty of places where this allows people to move really, really fast, really rapidly to get an idea out or iterate on an application without incurring that expense of really getting the database structure right without really even knowing what direction an idea is going in yet. So trade-offs, as we said before, and that's usually the trade-off that occurs here. The classic example of a document data store is MongoDB, but there's a million offerings now. All the major cloud providers have one, and you could go crazy looking at all the different ones, but MongoDB is still the most popular version of this. Then we get to the fun one. Julia, this is the answer to your joke. If you were hanging out in a Columnar bar, you'd still be able to get yourself a table, because this one has tables, columns, and rows. So this one feels the most like a SQL database. The main advantage here is it still hangs on to this whole scaling piece really well that traditional relational databases aren't really able to do. And the way they're able to achieve that is you group columns together. You come up with column families, and you basically say, hey, here's all the things that kind of relate to a customer, or here's all the things that kind of relate to an item, or here's all the things that relate to a delivery. And that happens within the context of a table. Why is this powerful? Well, instead of me having to write a bunch of joins, I can just say, like, look, I want to get all the info for this particular row or this unique identifier. And that's going to give me all the customer information, all the items information, all the delivery information. And then this is a little bit more low level, but it also allows for gaps in the data. Different rows don't have to adhere to the same contract. They don't have to have data for everything. And yeah, you could say, like, I can achieve that with nulls in a relational database, but what's happening a little bit lower level is those nulls still take up a little bit of space. So the algorithm that's storing this information on the actual storage of the server can be a lot more efficient with that storage. You can squeeze a lot more data in one place, and it's easier to replicate it out because now you can group certain families of data together that you know are often going to be requested together. I know that when I want some customer information, I'm probably going to get all the customer information. So why not group all that information together? And then the database algorithm under the hood can say, oh, this should belong together. So it's okay for me to create new versions of this database and only worry about these groups of information if I need to, if I'm growing that customer data faster than delivery data, for example. New columns can be added on the fly, much like I just talked about with the document schema. Generally, though, you're not losing out on some of that structure, though. It's kind of like you have that flexibility when the data is going in, but as you read it back out, you have a reliable schema. And it does a really great job of doing aggregate processing on massive amounts of data. Again, back to this whole family idea. If I want to grab, deliveries that occurred after, all deliveries that ended up occurring. I'm coming up with a bad example, but if you do minimum, maximum averages on some of the data sets here, it's very, very performant, and you can do some surprising stuff on a surprising amount of data. The classic example here, and the most popular one currently, is Cassandra. I feel like I should say, though, that's what DataStax uses under the hood, so maybe I'm a little biased here, but it is, the most popular one currently to date, but, full disclosure. All right, finally, of the big four that we're going to talk about today, the last one is the graph data stores. This one's super cool. This is what's at play for most like social network needs, but this is just all about like, hey, how do things relate to each other? You have an idea of a node and an edge, and any given node is like your entity, your thing, your users, your groups, your orders, your line items. And then how do those things relate to other things in the graph? You cannot define a thing without saying, how does this fit into the graph? And how does this fit into graph, or what is the relationship, is the edge. So you say, hey, look, in this example, the user Alice has a couple edges. She knows Bob. She has a relationship to Bob. Bob also knows her, so it's a two-way relationship or two-way edge. And then looking at the rest of the edges or relationships that Alice has, oh, she is a member of the chess group. And now we're using the same idea, same way to draw these relationship lines with completely different types of data. And that's where the power is. It makes things like find all employees who report directly or indirectly to Sarah like very trivial. It's like one line of code to get a very rich data set. And that's the use case for this type of thing. The most popular database right now for this is Neo4j. This is really intriguing to me, but that's kind of where my knowledge stops here. This is a place that I'd like to expand out more and understand, because I think this stuff is super cool. But quick note, if you're familiar with GraphQL, if you're like me, a front-end developer, or you're kind of stepping into that space, GraphQL is not a database. It's a query language. That's where the QL comes from. GraphQL can sit on top of a graph database. Generally speaking, it's trying to lay graph ideas on top of more traditional databases or other web services. It's just a tool.
I feel like this is like you could do like a funny, like if anybody's interested in this, like a funny like proof of concept for yourself and do like a 6 degrees of Kevin Bacon with this.
Yes, absolutely. And you'd be able to get the answer almost immediately. So I am ramping up, but I did want to check with you, Julia. How am I doing on time? Am I going over?
Nope, doing great.
Cool. So what should I use for my next project? That was overwhelming. That was a lot of information. These databases are all over the place, and they seem to be used for a lot of different things. And if you're thinking that, you would be correct. The answer to that question, though, is unfortunately, it depends what you're trying to do.
Looking for 6 degrees of Kevin Bacon, in which case.
Yeah, I mean, clearly, yeah. We come back to that previous slide. You always got to think about the trade-offs, right? But the trade-off I'm talking about here is probably not the one you're expecting. You got to ask yourself, what are your goals? And this isn't specific to this, but just generally speaking, something that has really been important to me in my journey in my professional life, particularly when it comes to learning new technologies. If you saw one of these and you're like, hey, I want to set up like an awesome 6 degree of Bacon like graph database. I really want to learn this technology. I want to see if I can pull this off. If that's your goal, I want to learn X technology. Simplify everything else. Make sure that every other piece that you have control over is something that you're familiar with, or at least somewhat comfortable with, because you want to spend most of that time learning that new technology. And if you find yourself fighting other pieces of your project, you're moving yourself away from your goal. You might still get there, but it's going to take you longer. So really learn one thing per pet project. And I would encourage pet projects for this type of exercise. I want to learn X technology. If it's, I want to build out an idea, then yeah, let's go back and reference what the strengths of these different databases are and go from there. But don't get too carried away. Pick whatever database is going to get out of your way the most. Either going to solve your problem the best, or even if a database might be an ideal solution for what you're trying to riff on, you're trying to get that idea out there. Don't get hung up on a technology choice, especially if you're not sure if you've really solidified that idea yet. Get something going. And so I would encourage you to pick whatever makes sense. If you're just like a relational database whiz, stick with it to get your idea out there. You can pick a simpler project to get your feet under you with a different NoSQL solution. If you really want to be like, okay, look, I think that either a NoSQL solution is the right move for this, or I just want to learn it and I'm, forget that, I can do both. Maybe a database as a service is the right move. There's a huge surge in off-the-shelf services right now, where you can just go and sign up for something, and at pretty low cost, you can just have a database sitting on one of these technologies that I just talked about without having to manage it. But again, just a quick call out to get that. If you want to build an idea, you want to get something going, you want to prove an idea out, see if it's going to work, pick the comfort stuff. Don't get hung up on these technology choices. And I know that's a bit of a detour from the rest of the talk, but this is something that I believe very passionately on, and encourage you to think in those terms. And then, from there, I will share this out. You don't have to take a picture or furiously write this down. But I do have a lot of next steps that might be helpful if you're really excited about this and want to dig in more. Recently, glitch.com, if you're familiar with it, announced database starter packs. And they're just building this collection out, but you can basically go on that website, sign up, click a button, and you have a fully baked starter with a database of your choosing ready to go. That's a great way to get started. Again, this does have DataStax underneath it for one of the starters, but you can ignore that and go in a different direction. And then I talked about those databases as a service. These are off the shelf. Hey, I'm going to sign up. I'm going to get this database. I'm going to connect my application to it. One of them is DataStax Astra. That's the product that I work on. So you can tell me all the things that are broken with it and that make you mad about it. I'd be happy to hear that. I believe MongoDB and Couchbase, which are two document-oriented solutions, both have databases as a service as well. And then, I'm sorry, a lot of the rest of these plugs are DataStax related. It wasn't on purpose. I just found a lot of good resources there. Tomorrow and Thursday, there's 2 free workshops to build a TikTok clone on top of this technology. That's build it in React with node packages and live with an instructor and people helping you out. So if that's interesting to you, that's free. Go sign up. Datastax.com/dev has a lot of free resources as well. And then a couple of write-ups that I found really helpful in just preparing for this talk, and just I felt like had pretty good overviews of the lay of the land. So check those out as well. I'll take a breath finally, and I know that was a whirlwind. First, let me apologize. It's been a long time since I've done a talk like this, so I probably glossed over quite a bit of context. So please keep me honest here with questions. And thank you so much for listening.